We already know the role of transport layer and the service that it provides. Let's quickly review what we have already learned about the transport layer. A transport layer protocol provides a logical communication between application process running on different hosts by logical communication. We mean that from an application's perspective, it is as if the host running these processes were directly connected. In reality, the host may be on opposite sides of the planet, communicated via numerous routers and wide range of link types. Application processes use the logical communication provided by the transport layer to send message to each other, free from the worry of the details of physical infrastructure used to carry these messages. This figure illustrates the notion of the logical communication. As shown in this figure, the transport layer protocols are implemented in the end system but not in the network routers. On the sending side, the transport layer converts the application layer message it receives from the sending application process into transport layer packets known as transport layer segments in internet terminology. This is done by breaking the application message into smaller chunks and adding a transport layer header to each chunk to create a transport layer segment. The transport layer then passes the segment to the network layer at the sending end, where the segment is encapsulated within a network layer packet and sent to the destination. It is important to note that the network routers act only on the network layer field of the diagram. That is, they do not examine the field of the transport layer segment encapsulated with the diagram. On the receiving side, the network layer extracts the transport layer segment from the datagram and passes to the segment up to the transport layer. The transport layer then processes the received segment, making the data in the segment available to the receiving application. More than one transport layer protocol may be available to the network application. For example, the internet has two protocols, TCP and UDP. Each of these protocols provide a different set of transport layer service to the invoking application.
Multiplexing and demultiplexing. In this, we discuss transport layer multiplexing and demultiplexing. That is, extending the host-to-host delivery service provided by the network layer to a process-to-process delivery service for applications running on the host. In order to keep the discussion concentrated, we will discuss this basic transport layer service in the context of the internet. We emphasize, however, that the multiplexing and demultiplexing service is needed for all computer networks. At the destination host, the transport layer receives segments from network layer just below. The transport layer has the responsibility of delivering the data in these segments to the appropriate application process running in this host. Let's take a look at an example. Suppose you are sitting in front of your computer and you are downloading web pages while running on FTP session and the two telnet sessions. You therefore have 4 network application processes running 2 telnet processes, 1 FTP process and 1 HTTP process. When the transport layer in your computer receives data from the computer layer below, it needs to direct the received data to one of these 4 processes. Let's now examine how this is done. First, recall from section 2.7 that's a process as part of the network application can have one or more sockets, doors through which data passes from network to the process and through which data passes from the process to the network. Thus, as shown in figure, the transport layer in the receiving host does not actually deliver data directly to a process, but instead to an intermediate socket, because at any given time there can be more than one socket in the receiving host. Each socket has a unique identifier. The format of the identifier depends on whether the socket is a UDP or a TCP socket, as we will discuss shortly. Now let's consider how a receiving host directs an incoming transport layer segment to the appropriate socket. Each transport layer segment has a set of fields in the segment for this process. At the receiving end, the transport layer examines these fields to identify the receiving socket and then directs the segment to the socket. This job of delivering the data in a transport layer segment to the correct socket is called demultiplexing. The job of gathering data chunks at the source host from different sockets and encapsulating each data chunk with header information that we will later be used in demultiplexing to create segments. and passing the segments to the network layer is called multiplexing. Note that the transport layer in the middle host in our figure must demultiplex segments arriving from network layer below to either process P1 or P2 above. This is done by directing the arriving segments data to the corresponding process socket. The transport layer in the middle host must also gather outgoing data from these sockets from transport layer segments and pass these segments down to the network layer. Although we have introduced multiplexing and demultiplexing in the context of the internet transport protocols, it's important to realize that they are concerns whenever a single protocol at one layer, at the transport layer or elsewhere, is used by multiple protocols at the next higher layer. To illustrate the multiplexing job, recall the household analogy in the previous section. Each of the kids is identified by his or her name. When Bill receives a batch of mail from the mail carrier, he performs a demultiplexing operation by observing to whom the letters are addressed and then hand delivering the mail to his brothers and sister. And performs a multiplexing operation when she collects letters from her brothers and sisters and gives the collected mail to the mail person.
Now that we understand the role of the transport layer multiplexing, demultiplexing, let us examine how it actually done in a host. From the discussion above, we know that the transport layer multiplexing requires first that socket have unique identifier and second that each segment has special fields that indicates the socket to which segment is to be delivered. This special field illustrated in the figure 3.3 are the source port number field and the destination port number field. Each port number is a 16-bit number ranges from 0 to 65535. The port number ranges from 0 to 1023 are called well-known port numbers and are restricted, which means they are reserved for use of well-known application protocols such as HTTP and FTP. The well-known port numbers is given in RFC 1700. When a new application is developed, we must assign the application a port number. It should now be clear how the transport layer could implement the demultiplexing services. Each socket in the host could assign a port number. And when a segment arrives at the host, the transport layer examines the destination port number in the segment and directs the segment to the corresponding socket. The segment's data then passes through the socket into attached process. As well, we see this is a basically how the UDP does it.
As shown in figure 3.4, the inversion of source and destination port numbers in the A to B segment, the source port number serves as a part of a return address. When B wants to send a segment back to A, destination port in the B to A segment will take its value from the source port value of the A to B segment. As an example, recall the UDP server program udpserver.py. The server uses the recursive function form method to extract the client-side port numbers from the segment it receives from the client. It then sends a new segment to the client with the extracted source port number serving as a destination port number in this new segment.
Situation illustrated in figure 3.5, in which host C initiates two HTTP sessions to server B and host A initiates one HTTP session to B. Hosts A and C and server B each have their own unique IP address A, C and B respectively. Host C assigns two different source port numbers 26145 and 7532 to its two HTTP connections. Because host A is choosing source port numbers independently of C, it might also assign a source port of 26145 to its HTTP connection, but this is not a problem. Server B will still be able to correctly demultiplex the two connections having the same source port number, since the two connections have different source IP addresses.
UDP checksum. As shown in the below figure of UDP segment structure, the UDP stands for User Datagram Protocol. So the UDP checksum provides for error detection. You know, that is the checksum used to determine whether bits within the UDP segment has been altered. Say for example, maybe because of voice in the links or while stored in a router. As it is moved from source to destination, UDP at the sender side performs the ones complement of the sum of all the 16-bit words in the segment with any overflow encountered during the sum of being wrapped around. So this result is put in the checksum field of the UDP segment. So the small example which is shown in the page number 203, it explains the checksum calculation. You may wonder why UDP provides a checksum in the first place. As many links layer protocols, even including the popular Ethernet protocol, also provides error checking. The reason is that there is no guarantee that all the links between source and destination provide error checking. That is, one of the links may use a link layer protocol that does not provide error checking. Furthermore, even if segments are correctly transferred across a link, it's possible that bit errors could be introduced when a segment is stored in a router's memory. Given that neither link by link reliability nor in memory error detection is guaranteed, so UDP most provide error detection at the transport layer on an end-to-end basis. If the end-to-end data transfer service is to provide error detection, this is an example of the celebrated end-to-end principle in the system design, which states that since certain functionally maybe like error detection in this case may be implemented on an end-to-end basis, functions placed at the lower levels may be redundant or of little value when compared to the cost of providing them at the higher level. Because of IP is supposed to run over just above any layer 2 protocol, it is useful for the transport layer to provide error checking as a safety measure. Although UDP provides error checking, it does not do anything to recover from an error. Some implementations of UDP simply discard the damaged segment. Others pass the damaged segment to the application with a warning. This wraps up our discussion of the UDP. We'll soon see the DCP offers reliable data transfer to its application as well as the other services that UDP does not offer.
Enable data transfer service model and the service implementation interface for our data transfer protocol. The sending side of the data transfer protocol will be invoked from by above by a call to the real data transfer send. It will pass the data to be delivered to the upper layer at the receive side. Here the real data transfer stand for the reliable data transfer protocol, and send indicates that the sending side of the reliable data transfer is being called. The first step is developing any protocol is to be choice of the good name. On receiving side, the real data transfer of the receive will be called when the packet arrives from the receiving side of the channel. When the real data transfer protocol wants to deliver the data to the upper layer, it will do so by the calling to be delivered data. In the following, we use the terminology packet rather than the transfer layer segment because the theory of the develop in this section that applies to the computer network in the general and not just to the interest transfer layer. The generic term packet perhaps the more appropriate here. In this section we consider only the case of the unconditional data transfer, that is data transfer from the sending to the receiver side. The case of the reliable bidirectional, that is the full duplex data transfer, is the conceptually the no more difficulty but consider the two more tedious to the explain.
Figure 3.11 shows the FSM description for RDT 2.1. Data transfer protocols including TCP is to add a new field to the data packet and have the sender number its data packets by putting a sequence number into this field. The receiver then need only check this sequence number to determine whether or not the received packet is a retransmission. For this simple case of a stop and wait protocol, a 1-bit sequence number will suffice, since it will allow the receiver to know whether the sender is resending the previous transmitted packet. The sequence number of the received packet has the same sequence number as the most recently received packet, or a new packet. ACK and NAK packet do not themselves need to indicate the sequence number of the packet they are acknowledging. The sender knows that a received ACK or NAK packet was generated in response to its most recently transmitted data packet. Sender and receiver FSMs each now have twice as many states as before. This is because the protocol state must now reflect whether the packet currently being sent by the sender or accepted at the receiver should have the sequence of 0 or 1. Protocol RDT 2.1 uses both positive and negative acknowledgements from the receiver to the sender. We can accomplish the same effect as NAK if, instead of sending a NAK, we can send an ACK for the last correctly received packet. A sender that receives two ACKs for the same packet, that is, receives duplicate ACKs, knows that the receiver do not correctly receive the packet following the packet that is being ACKed twice.
Simple solution to achieve a reliable data transfer is by adding a new field to the data packet and have a sender number its data packet by putting a sequence number into this field. Now we're going to discuss about the protocol RTD 2.1, that is reliable data transfer 2.1. It uses both positive and negative acknowledgements from the receiver to the sender. When an out of the order packet is received, the receiver sends a positive acknowledgement for the packet it has received. When a corrupted is received, the receiver sends a negative acknowledgement. We can accomplish the same effect as negative acknowledgement if, instead of sending a negative acknowledgement, we send an acknowledgement for the last correctly received packet. A sender that receives two acknowledgements for the same packet knows that the receiver did not correctly receive the packet following the packet that is being acknowledged twice. Over a negative acknowledgement free reliable data transfer protocol for a channel with bit error is RTD 2.2 as shown in the figure, and one subtle change between RTD 2.1 and RTD 2.2 is that the receiver must now include the sequence number of the packet being acknowledged by an acknowledgement message, and the sender must now check the sequence number of the packet being acknowledged by a received acknowledgement message. This is done by including the 0 or 1 arguments in is acknowledgement function in the sender FSM.
Reliable data transfer sender. It works in 4 states. State 1, top left. In the figure, top left state called wait for 0 is the start state waits until it receives a message from the upper application layer. After it is received as the transport layer, it adds a transport layer header added with the sequence number 0 sent into the network. State 2, top right. In this state, protocol checks whether the packet acknowledgement is correct or sequence 1 is received as acknowledged. In this case, the sender resends the packet as the transmitted sequence is not equal to the received. If the sender receives a non-current and correct sequence number, it moves to the next state. State 3, bottom right. In the figure, top left state called wait for 1 waits until it receives a message from the upper application layer. After it is received as transport layer, it adds a transport layer header added with sequence number 1 sent into the network. State 4, bottom left. In this state, protocol checks whether the packet acknowledgement is corrupt or sequence 0 is received as acknowledged. In this case, the sender resends the packet as the transmitted sequence is not equal to the received. If the sender receives a non-corrupt and current corrupt sequence number, it moves to the next state.
15 RTD 3.0 sender. RTD 3.0 is the last and best version of reliable data transfer protocol. Before RTD 3.0, RTD 2.2 was introduced to account for the channel with bit error, in which bit error can also occur in acknowledgement. As the design of RTD 2.2 is the stop and wait for protocol. If there is a network issue and the acknowledgement or packet is lost, the sender waits infinitely for it. How RTD 3.0 solve this problem? RTD 3.0 introduces a timer at the sender side if the acknowledgement is not received within a particular time. The sender resends the packet. This method solves the issue of packet loss. This is the representation in a finite state machine. In this have mainly 4 state. State 1 is the top left. This is the start state in a sender FSM, which is called wait for call 0 from above. It wait till it receive a message to start from the application layer. In this state, the datagram is created with the sequence number 0 in its header and payload as a message in its body. Finally, the packet is pushed into the network and execution moves to the next state. State 2 is the top right. This state confirms whether the receiver has received the packet or not. State check that if the received acknowledgement is not corrupt as the sequence number 1 and is reached within the time. If these two criteria are satisfied, the execution moves to the next state, else the state resends the packet. State 3 is the bottom right. This state in the sender FSM is called wait for a call 1 from above. It waits till it receives a message to start from the application layer. In this state, the datagram is created with the sequence number 1 in its header and payload as a message in its body. Finally, the packet is pushed into the network and execution moves to the next state. State 4 is the bottom left. This state confirm whether the receiver has received the packet or not. State check that if the received acknowledgement is not corrupt, has the sequence number 0 and is reached within the time. If these two criteria are satisfied, the execution moves to the next state, else the state resends the packets.
RDT 3.0 means Reliable Data Transfer version 3.0. The required functionalities are error detection mechanism, receiver feedback, data sequence number, acknowledgement carries data sequence number, timeout timer. In this case, sender waits reasonable amount of time for acknowledgement, retransmits if no acknowledgement received in this time. If the packet or acknowledgement just delayed, retransmission will be duplicate. Sequence numbers helps to resolve this. RDT version 3.0 protocol is also called stop and wait protocol and alternating bit protocol because we can alternate between 0 and 1 sequence numbers. In figure 3.16, first one is operation with no loss. So when there are no losses, things are straightforward. If you send packet 0, acknowledgement will acknowledge the packet 0, and if you send the packet 1, then acknowledgement 1 is getting. Because in this case there is no loss of packet and there is no loss of acknowledgement. So here is a case where packet is lost. When packet is lost, we are not going to receive any acknowledgement. Therefore, you should wait for some time till timeout. Then you can retransmit the same packet. And response to this is you can get a acknowledgement. And again things go on as usual. And third one is operation of RDT 3.0 with lost acknowledgement. So here is a case where acknowledgement is lost. Because of this, sender doesn't know the status of the packet, whereby again it is timeout, sender resends the packet. In this case, packet happens to be duplicate because original packet already reached the receiver. In this case, receiver uses the sequence number to identify the duplicate packet and it is going to be discard that packet. In spite of this, receiver still sends an acknowledgement. Because of this, sender knows the retransmission of packet is successful. And the last one is operation of RDT 3.0 with premature timeout. In this particular case, you send an packet 0. In response to this packet, you are sending an acknowledgement from receiver. But unfortunately, acknowledgement got deleted. So what is happening in this center? You are timed out even before the reception of acknowledgement. So you have to retransmit the same particular packet again. When this duplicate packet 0 arrives at the receiver, what should the receiver do? Since this is a duplicate, it should definitely discard that packet. And the main question is, should it send the acknowledgement or not? Then it should send the acknowledgement because it is conceivable. Since the previous acknowledgement was lost and packet 0 is retransmitted due to timed out, and thereby sender needs to know the retransmission of packet 0 was successfully received at receiver. Hence it is important to send the acknowledgement again.
Let's see the stop and wait protocol and pipeline protocol. Stop and wait protocol means the sender provides the recipient desired data. The sender pauses after transferring the data and waits for the receiver acknowledgement for his transmission. Stop and wait protocol, which is a flow control protocol, uses data link layer flow control functionality. And pipeline protocol is the process of storing and prioritizing computer instruction that the process executes. It happens in a continuous, orderly, somewhat overlapped manner. To appropriate the performance impact of stop and wait protocol behavior is to consider an idealized case of two hosts, one located on western coast of United States and other located on east coast, as shown in the figure 3.17. The speed of light round trip propagation delay between two end systems. Adaptability is approximately 30 milliseconds. Suppose that they can connect it by channel with transmit rate R of 1 Gbps, which is 10 to 9 bits per second, with a packet size L of 100 per packet. Including both header field and data, the time need to actually transmit the packet into the 1 Gbps link as D transmission is L by R, which is 800 bits by packet by 10 to 9 bits per second, which is 8 microseconds. Now see the stop and wait sending and pipeline sending. With our stop and wait protocol, if the sender begins sending the packet at t is 0, then at t is L by R, which is 8 microseconds. The last bit enters the channel at the sender side. The packet then hits 15 microseconds across the country journey, with the last bit of packet emerging at the receiver at t is RTT by 2 plus L by R, which is 15.008 m seconds. Assuming for simply that acknowledgement packets are extremely small and that the receiver can send acknowledgement as soon as the last bit of data packet is received, the acknowledgement emerges that the sender is at t is RTT by R plus L, which is 30.008 m seconds. At this point, the sender can now transmit the next message. Thus, in 30.008 milliseconds, the sender was sending for only 0.008 m seconds. If we define the utilization of sender as the fraction of time the sender is actually busy sending his bits into the channel. The analysis of stop and wait protocol has rather dismal sender utilization as U sender is L by R plus R double T plus L by R is 0.008 by 30.008, which is equal to 0.00027. Now see the pipeline sending. The solution of this particular performance problem is simple. Rather than the operate in stop and wait manner, the sender is allowed to send multiple packets without waiting for acknowledgements, as shown in figure 3.17b and 3.18b. Shows that if the sender is allowed to transmit 3 packets before having to wait for acknowledgement, the utilization of sender is essentially tripled, since the many in transit sender to receive packets can be visualized as filling a pipeline. This technique is known to be as pipelining. The pipelining has the following consequence for reliable data transfer protocols, which are the range of sequence numbers must be increased. The sender and receiver sides of protocols may have to buffer more than that one packet. Two basic approaches toward pipeline recovery can be identified as go back and selective repeat.
Go backend protocol. In a go backend protocol, the sender is allowed to transmit multiple packets when available without waiting for an acknowledgement, but is constrained to have no more than some maximum number which is allowed n of unacknowledged packets in the pipeline. Figure shows the sender's view of the range of sequence numbers in a go backend protocol. If we define base to the sequence number of the oldest unacknowledged packet and the next sequence number to be the smallest unused sequence number, that is the sequence number of the next packet to be sent, then four intervals in the range of sequence numbers can be identified. Numbers in the interval 0 base minus 1 correspond to packets that have already been transmitted and acknowledged. The interval base next sequence number minus 1 corresponds to the packets that have been sent but not yet acknowledged. Sequence numbers in the interval next sequence number base plus n minus 1 can be used for packets that can be sent immediately. Should data arrive from the upper layer, finally, sequence number greater than or equal to base plus n cannot be used until an acknowledged packet currently in the pipeline has been acknowledged. As suggested by figure, the range of permissible sequence numbers for the transmitted but not yet acknowledged packets can be viewed as a window of size n over the range of sequence number. As the protocol operates, this window slides forward over the sequence number space. For this reason, n is often referred to as the window size and the go backend protocol itself as a sliding window protocol.
Figure number 3.22 shows the operation of GBN protocol for the case of a window size of the 4 packets. Because the window size of the limitations, the sender sent packets 0 through to 3, but then must wait for a one of more packets. These are acknowledged before proceeding as each successive acknowledgement. For example, acknowledged 0, acknowledged 1 is received. The window slides forwarded and sender can transmit a new packet 4 and packet 5 respectively. On the receiver side, packet 2 is lost, thus the packet 3, 4, 5 are found to be out of the order and are discarded. Before closing off our discussion of go back n, it is worth noting that an implementation of this protocol is a protocol stack would like have structure similar to that of extended FSM in figure 320. The implementation would also be in form of various procedures that implement the actions to be taken in response to the various slacks. Implementation of various slacks. In the such based event based programming, the various procedures are called invoked either by the procedure of the protocol stack or such by the real interrupt in the center of the events would one a call from upper layer entity invoked ready ready to send, and interpret third call from the ready to receive. When packet arrives, the programming exercise at the end of this chapter will be give a chance to actually implement these routines in simulated but realistic networking settings. We note here the go back and protocol incorporate almost all the techniques that have encountered when we study and reliable data transfer community contents in 3.5 section of TCP. This technique includes the use of sequence numbers, communicative acknowledgements, checksums, and timeout retransmit operations.
The selective repeat sender and receiver views of the sequence number space shows the SR sender view of the sequence number space. The SR receiver will acknowledge a correctly received packet whether or not it is in order. Out of order packets are buffered until any missing packets are received, at which point a batch of packet can be delivered in order to the upper layer. For example, if there is no ACK for packet send base propagating from the receiver to the sender will eventually transmit packet send base even though it is clear that the receiver has already received the packet. Now let us see what are the events and actions that are taking place at the SR sender side. The first one is data received from above. When data is received from the above, the SR sender checks the next available sequence number for the packet. If the sequence number is within the sender's window, the data is packetized and sent. Otherwise, it is in either buffered or returned to the upper layer for later transmission as in GBN. Second one is timeout. Timers are again used to protect against lost packets. However, each packet must now have its own logical timer since only a single packet will be transmitted on timeout. Third one is ACK received. If an ACK is received, the SR sender marks that the packet has having been received, provided it is in the window. If the packet sequence number is equal to send base, the window base is moved forward to the acknowledged packet with the smallest sequence number. Some of the events and actions that are taking place at the SR receiver side that are packet with sequence number in RVC base plus n minus 1 is correctly received. In this case, the received packet falls within the receiver's window and a selective acknowledgement packet is returned to the sender. If the packet was not previously received, it is buffered. If this has a sequence number equal to the base of receive window, then this packet and any previously buffered and consecutively numbered packets are delivered to the upper layer. Packet with sequence number in RVCV base and RCV base minus 1 is correctly received. In this case, an ACK must be generated even though this is a packet that the receiver has previously acknowledged. Third one, otherwise you ignore the packet. If the receiver were not acknowledged this packet, the sender's window would never move forward. This example illustrates an important aspect of SR protocols. The sender and receiver will not always have an identical view of what has been received correctly and what has not.
SR operation. The figure shows an example of SR operation in the presence of lost packet. The lack of synchronization between sender and receiver window has important consequence when we are faced with the reality of finite range of sequence number. Consider what could happen, for example, with a finite range of 4 packet sequence number 0, 1, 2, 3 and window size 3. Suppose packet 0 through 2 are transmitted and correctly received and acknowledged at receiver. At this point, the receiver window is over 4, 5th and 6th packet.
which have a sequence number 3, 0 and 1 respectively. Now consider two scenarios. In the first figure, the ACK for first 3 packets are lost. The sender retransmits these packets. The receiver thus next receive packet with sequence number 0, a copy of the first packet sent. The second figure shows ACK for the first 3 packets are all delivered correctly. The sender thus moves its window forward and sends 4th, 5th and 6th packet with sequence number 3, 0 and 1 respectively. The packet with sequence number 3 is lost, but the packet with sequence number 0 arrived. A packet containing new data. Now consider the receiver viewpoint, which has a figurative between sender and receiver. Since the receiver cannot see the action taken by sender, all the receiver observes the sequence of message it receives from channel and sends into channel. As far as it concerned, two similar figures are identical. This is no way of distinguish the retransmission of the first packet from the original transmission of the fifth packet clearly. A window size that is one less than size of the sequence number space would work. But how small must window size be? A problem at the end of the chapter. You to show that window size must be less than or equal to half of the size of the sequence number space of SR protocol.
TCP send and receive buffer. Once a TCP connection is established, the two application processes can send the data to each other. Let's consider the sending of the data from the client process to the server process. The client process passes the stream of data through the socket. As described in the section 2.7, once the data is passed through the door, the data in the hands TCP running in the clients. As shown in the figure 3.28, TCP directs its data to the connection sends buffer, which is the one of the buffer that has set of asset during the initial three-way handshake. From the time to time, TCP will grab chunks of the data from the send buffer to the pass the data to network layer. Interestingly, the TCP specification RFC 793 is a very light back about specifying when TCP should actually send the buffered data. Starting, the TCP should send the data in the segments at the own convenience. The maximum amount of data that can be grabbed and placed in the segment is limited by the maximum segment size MSS. The MSS is typically set of the first determining the length of largest link layer frame that can be sent by the local sending host. The so-called maximum transmission unit MTU and then setting the MSS to ensure that the TCP segment will fit into the single link layer frame. Both Ethernet and PPP link layer protocols have MSS of 1500 bits. Approaches have also been proposed to discovering the path of MTU, the largest link layer frame that can be sent the link from one source to destination. RFC 1191 is setting the MSS based on the path MTU value. Note that the MSS is the maximum amount of application layer data in the segment, not a maximum size of TCP segment including the headers. TCP pair each of chunk of clients of data with the TCP header, thereby forming the TCP segments. The segments are passed down the network layer where they are separately encapsulated within the network layer IP datagrams. The IP datagrams then sent into the network. When TCP receives the segment of the other end, segment data placed in the TCP connection received buffer as shown in the 3.28 figure. The application reads the stream of the data from this buffer. Each side of connection has its own send buffer and its receive buffer. When we see the discussion of the TCP connection consists of the buffers in variables and the socket connections to process the one host and the set of buffers variables and socket to the process of another host. As mentioned earlier, no buffer or variables are allocated to the connection in the network elements like switches, routers, and the repeaters between the hosts.
This is the diagram of TCP segment structure. In that source port 16 bits, it indicates the sender application port number. Destination port 16 bits, it identifies the recipient application port number. Sequence number 32 bits, it represents the byte number of the first byte in the segment. It is used to order and reassemble segment at the receiver. Acknowledgement number 32 bits, it acknowledges the recipient of the data by indicating the next expected sequence number. It is only used when the acknowledgement flag is set. Data offset 4 bits, it indicates the length of the TCP header in 32-bit words. Since TCP header size can vary, field specifies the offset to start the TCP data. Reserved 16 bits. These bits are reserved for future use and currently set to 0. Control flag. In that, urgent flag that indicates if urgent pointer field is valid. Acknowledgement flag indicates the acknowledgement number field is valid. Push flag requests the receiving TCP to push the data to the recipient application immediately. Reset flag resets the collection. Synchronize initiate a connection establishment. Finish flag terminates the connection. Window size 16 bits. It specifies the size of the receiving windows, which indicates the number of bytes sender can transmit before receiving an acknowledgement. Checksum 16 bits provides error detection for the TCP segment header and data. Urgent pointers 16 bits. It pointers to the last byte of urgent data in the segment if the urgent flag is set. Options: variable length if present. This field carries additional TCP options such as maximum segment size, window scale, and timestamps. Padding 32 bits. It is used to ensure that TCP header ends on a 32-bit boundary when the options are present. Data. This field carries actual data being transported by the TCP segment. It's important to note that TCP segment structure described here represent a general format, but actual implementation may vary depending on specific network protocols and implementation.
Telnet, a case study for sequence and acknowledgement numbers. Telnet, defined in RFC 854, is a popular application layer protocol used for remote login. It runs over TCP and is designed to work between any pair of hosts. Unlike the bulk data transfer applications discussed in Chapter 2, Telnet is an interactive application. We discuss a Telnet example here as it nicely illustrates TCP sequence and acknowledgement numbers. We note that many users now prefer to use the SSH protocol rather than Telnet since data sent in Telnet connection is not encrypted. Suppose host A initiates a telnet session with host B. Because host A initiates the session, it is labeled the client and host B is labeled the server. Each character typed by the user, that is at the client, will be sent to the remote host. The remote host will send back a copy of each character which will be displayed on the telnet user's screen. This echo pack is used to ensure that characters seen by the telnet users have already been received and processed at the remote site. Each character thus traverses the network twice between the time the user hits the key and the time the character is displayed on the user's monitor. Now suppose the user type a single character or a letter C and then grabs a coffee. Let's examine the TCP segments that are sent between the client and server. As shown in figure 3.31, is suppose the starting sequence number are 42 and 79 for client and server respectively. Recall that the sequence number of a segment is a sequence number of the first byte in the data field. Thus, this first segment sent from the client will have sequence number 42. The first segment sent from the server will have sequence number 79. Recall that the acknowledgement number is the sequence number of the next byte of the host is waiting for. After the TCP connection is established, but before any data is sent, the client is waiting for byte 79 and the server is waiting for byte 42. As shown in the figure 3.31, three segments are sent. The first segment is sent from the client to the server containing the 1 byte ASCII representation of the letter C in its data field. This first segment also has 42 in its sequence number field as we just described. Also, because the client has not yet received any data from the server, this first segment will have 79 in its acknowledgement number field. The second number segment is sent from the server to the client. It serves a dual purpose. First, it provides an acknowledgement of the data the server has received. By putting 43 in the acknowledgement field, the server is telling the client that it has successfully received everything up through byte 42 and is now waiting for byte 43 onward. The second purpose of the segment is to echo back the letter C. Thus, the second segment has the ASCII representation of C in its data field. This second segment has the sequence number 79, the initial sequence number of the server to client data flow of this TCP connection, as this is the very first byte of data that the server is sending. Note that acknowledgement for client to server data is carried in a segment carrying server to client data. This acknowledgement is said to be piggybacked on the server to client data segment. The third segment is sent from the client to the server. Its sole purpose is to acknowledge the data it has received from the server. That is, recall that the second segment contained data, the letter C, from the server to the client. This segment has an empty data field. That is, the acknowledgement is not being piggybacked will any client to server data. This segment has 80 in the acknowledgement number field because the client has received the stream of bytes up through byte sequence number 79 and is now waiting for byte 80 onward. You might think it odd that this segment also has a sequence number since the segment contains no data, but because TCP has a sequence number field, the segment need to have some sequence number.
Figure 3.35 Segment 100 not retransmitted. Here, in this figure, host A sends two segments back to back. The first segment has a sequence number 92 and 8 bytes of data, and the second segment has a sequence number 120 bytes of data. Suppose that both segments arrives intact at B, and B sends two separate acknowledgements for each of these segments. The first of these acknowledgements has an acknowledgement number 100. The second has the acknowledged number 120. Suppose now that neither of the acknowledgement arrives at the host A before the timeout. When the timeout event occurs, host A resends the first segment to the sequence number 92 and restarts the timer. As long as the acknowledgement for the second segment arrives before the new timeout, the second segment will not be retransmitted. In the third and the final scenario, suppose host A sent two segments exactly as the second example. The acknowledgement of the first segment is lost in the network, but just before the timeout event, host A receives an acknowledgement with the acknowledgement number 120. Host A therefore knows that host B has received everything up to the byte 119. So host A does not resend either of the two segments.
We begin this chapter by studying the services that a transport layer protocol can provide the network applications. At one extreme, the transport layer protocol can be very simple and offer a non-frill service to the applications, providing only a multiplexing, demultiplexing functions for communicating process. The Internet's UDP protocol is an example of such a no-frills transport layer protocol. At the other extreme, a transport layer protocol can provide a variety of guarantees to applications such as reliable delivery of data, delay guarantees, and bandwidth guarantees. The services that a transport protocol can provide are often constrained by the service model of the underlying network layer protocols. If the network layer protocol cannot provide delay or bandwidth guarantees to transport layer segments, then the transport layer protocol cannot provide delay or bandwidth guarantees for messages sent between processes. We learned in section 3.4 that a transport layer protocol can provide a reliable data transfer even if the underlying network layer is unreliable. We saw that providing reliable data transfer has many stable points, but that the task can be accomplished by carefully combining acknowledgements, timers, retransmissions, and sequence numbers. Although we covered reliable data transfer in this chapter, we should keep in mind that reliable data transfer can be provided by a link, network, transport, or application layer protocols. Any of the upper four layers of the protocol stack can implement acknowledgements, timers, retransmissions, and sequence numbers and provide reliable data transfers to the layer above. In fact, over the years, engineers and computer scientists have independently designed and implemented link, network, transport, and application layer protocols that provide reliable data transfer. In section 3.5, we took a close look at TCP, the Internet Connection Oriented and Reliable Transport Layer Protocol. We learned that TCP is complex, involving connection management, flow control, and round-trip time estimation, as well as reliable data transfer. In fact, TCP is actually more complex than our descriptions. We intentionally did not discuss a variety of TCP patches, fixes, and improvements that are widely implemented in various versions of TCP. All of this complexity, however, is hidden from the network application. If a client on one host wants to send data reliably to a server or another host, it simply opens a TCP socket to the server and pumps data into the socket. The client-server application is blissfully unaware of a TCP's complexity. In section 3.6, we have examined congestion control from a board perspective, and in section 3.7, we showed how TCP implements congestion control. We learned that congestion control is the imperative of the well-being of the network. Without congestion control, a network can easily become gridlocked without little or no data being transported end-to-end. In this section 3.7, we learned that the TCP implements an end-to-end congestion control mechanism that adaptively increases its transmission rate when TCP connections path is judged to congestion-free and multiplicated decreases its transmission rate when loss occurs. We also examined in some depth that impact of a TCP connections establishment and a slow start on latency. We observed that in many important scenarios, connection establishment and a slow start significantly contribute to end-to-end delay.
We emphasize once more that while TCP congestion control has evolved over the years, it remains an area of intensive research and will likely continue to evolve in the upcoming years. Our discussions of specific internet transport protocols in this chapter has focused on UDP and TCP, the two workhorses of the internet transport layer. However, 2 decades of experience with these two protocols has identified circumstances in which neither is ideally suited. Researchers has been busy developing additional transport layer protocols, several of which are now IETF proposed standards. In chapter 1, we said that a computer network can be partitioned into network edge and network core. The network edge covers everything that happens in the end systems. Having now covered the application layer and the transport layer, our discussions of a network edge is complete. It is time to explore the network core. That this journey begins in the next chapter, where we will study the network layer and continues into chapter 5, where we will study the link layer. Thank you.